Yeah, you should put it to the ground and I can take care of the rest.
Okay, awesome. Sasha, say something so the camera will focus on you.
All right, very good.
Good.
Yeah, so I'm very happy to be invited to give this talk in our own topology seminar. I'm your own Sasha Voronov, own topology seminar, and I will be talking about the exceptional symmetry of group spaces. Title. It's a joint paper with Sasha Sasha. It's a common co-author for both Craig Westerland and myself. I kind of inherited the co-authorship from Craig, and the title is really cheating in every single word, basically. The exceptional symmetry is not the exclusive symmetry, it's the exceptional in as a math term, the exceptional group symmetry. And loop spaces is not all loop spaces, it's certain types of loop spaces. And then it will be not as much cheating in this case. So first of all, let me introduce the background of the subject. So we were inspired by physics discovery of mysterious duality. So the whole thing is inspired by physics mysterious duality. And we, Satya, with Hisham, we started discovering, finding interesting things in certain loop spaces, interesting structures that happen to be there for loop spaces, for certain types of loop spaces, and those structures which had not been noticed. And so basically the idea is that in physics, the root systems of type ek, where k runs from 0 to 8 through 8. And these are root systems of this exceptional type ek, root systems from I don't know, combinatorics or Lie theory, that they in physics, and this is 2001 finding of Iqbal Nightscape. They said that they noticed that oh wait, yeah, this part, yeah, okay. So this part is physics. So these are if you look at deep brains in compactification of dimensional reductors, patients, / dimensional reductors of M theory. And M theory is sort of the ubiquitous theory that covers everything of interest in recent quantum field theory, such as it's an 11th theory, and it covers all sorts of string theories and supergravities, you name it. It was, I think, proposed by Newton, and the story is that M stands for W upside down. So they noticed that root systems show up there, and so it's those compactifications and dimensional reductions, they reduce to dimensions 11 minus k, and this k corresponds exactly to this. So they notice some combinatorial pattern happening for those objects of interest, deep brains in those theories happening depending on what your k is, how many dimensions you reduce from 11-dimensional M theory down. Then you would be able to see the root system of type EK playing a prominent role there. Well, they related this, and the mysterious duality, they related this to a very classical mathematical pattern of Delpezza surfaces. Delpezza surfaces. And that was it had been known for a long time that that root systems of type EK play a prominent role in the geometry of Delpezza surfaces. Delpezza surfaces run like this. You start with CP2 as the simplest Delpezza surface with a complex projective plane, and then you start blowing up points on it. So if you blow up 1 point, yeah, we call this B0. If you blow up 1 point, then so this is like for the topologist, blow up the algebraic geometric blow up of a point is the same as taking the connected sum of CP2 with one. The same copy of CP2, in which you change the complex structure to its opposite. So I gets multiplies now vectors in potential space by negative I, and then you take the connected sum. And then you just take the algebraic geometric blow up of 1 point. You glue in a copy of CP1 instead of this point, glue in according to how the lines around this point are coming to this point, and they will be glued to different points of this new extra line that you glue in CP1. And then you glue 2 points. You blow up 2 points. In other words, you take another connected sum with another copy of CP2 bar, and you get 2 B2 and so on. And you can do it in an unlimited way, but when you hit B8, the list of Delpezza surfaces stops. You get complex compact surfaces, but all in one. But then all you call Delpezzas if you blow up more than 8 points. They lose their Delpezzaness property, the Fana property, that the anti-canonical class is ample. Now there's also an outlier surface, which I want to sketch below. Yeah, so and the same process of, if you blow up 1 point on it, you get B2, but it's CP1 or CP1. It's another Delpezza surface, which is not on this list, but if you blow up 1 point on it, you get B2. So, and then there is the geometry of those surfaces is nicely related to the root systems of type EK. It is related to the intersection theory of divisors in those surfaces. Maybe I shouldn't even mention this word in the topology seminar. It's related to the intersection theory of defined on homology, on integral homology of surfaces. So the integral homology makes up a lattice in the real homology, and then for those surfaces, it turns out it's a lattice in those cases, and then because of the intersection numbers, this lattice acquires a non-degenerate integral symmetric bilinear form on H2. And so you get an H2 of A C. You get an inner line. integral valued inner product. And so you get a lattice with an inner product, and this gives you a lot of combinatorics. And it turns out this inner product is of Lorentzian type. Again, I'm using the physics word, but it's mathematics, right? It's this. It's not a symmetric. It's not a positive definite symmetric bilinear form of the inner product, but it's actually of mixed index. So it has one negative. It has one positive mode, and all the others are negative. So it has the positive index is one, the others is negative. And actually, this group is actually similar to z to the power k plus one. So one component is it has a negative inner product, the positive inner product, all others are negative. Sense is Lorentzian type. And then there's also something else there. Namely, there is something else coming from algebraic geometry. Namely, if you take the canonical class, maybe I should call it K. The canonical class of B is K. Then it becomes a distinguished element. Well, it's meaning the first Chern class of the potential bundle. C1 of the whole of the potential bundle of B K. Then it gives you some distinguished elements in H would be K. Z. And this is another ingredient that that allows you to construct to sort of find the root system of type K and so on. And I said so here I'm kind of hinting on where the construction in algebraic geometry is coming from. The construction given that it has a surface, how you can construct a lattice. This is the lattice in RK plus one. And how you and so the lattice has a non-degenerate inner product of Lorentzian type, and also there is a particular element of this lattice, some kind of distinguished element of this lattice, which allows you to do things, to do interesting things with this and construct, which gives you all the combinatorics you need. For instance, you can construct the root system as sitting in here. It will be a finite set of elements on this lattice, which turns out to be a system of roots in this ambient RK plus one, and it's just given by elements which are, so for instance, RK, a root system of type PK is obtained by just taking elements on this lattice, I don't know, X and H2 B A C, right? That X, the inner product of X and K became it's zero, so that they should be by their orthogonal complement of the lattice, and such that their inner product is, I think in this case, it's negative 2. No, it's actually negative 2 positive. I think it's negative 2. Yeah.
But one or the other, and if you've got it wrong, well, it's just the other.
Exactly. Yeah. So this way it's a finite, and the thing is that it's a finite set as long as k is less than or equal to 8. When k hits 9, it becomes an infinite set, and becomes a system of roots actually of an affine Lie algebra of the corresponding type like ek hat. E8 hat or E9. So this is one thing, and so the physicist said, well, there must be something deep going on, like in this case, quantum between deep ranges in the Hesse surfaces, but nobody has been able to find out what deep is going on and why there is this certain correspondence between those two subjects, those two constructions. But what we did with Sasha, so this is classical math, classical calculation. Yeah, maybe one word related to the prominence of the root systems of type PK. So, for example, you get 27 lines on a cubic surface in B3, in CP3. Or a smooth cubic surface. Smooth cubic surface in CP3, and this is actually B6 on the list. Okay, so the cubic surface is surface of degree 3, right? Yeah, so it's 9. Right, and let's give it surface of B6. There is classical result of the 19th century mathematics that there are 27, exactly 27 lines on every smooth cubic surface in CP3. And it comes out of the fact, I mean, it's related, it may be proven actually through the fact that basically 27 is the dimension of a fundamental representation of, let's say, the Lie algebra of type 6. So that's one. Yeah, what we did with Sasha was to relate it, and we call it mysterious triality, to relate it to at first, and I already reported about this in the seminar. So it's Sasha, and this is a paper in Communications in Math Physics, in which was published this year, 2023. We called mysterious triality and rational homotopy theory. So we found the same pattern of root systems for the same combinatorics in a sequence now of objects, not of algebraic geometry, but more of topology. And that was, we're looking at the sequence of the sphere S4, the cyclic loop space of the sphere S4, and iterated cyclic loop spaces from squared S4, and so on. Again, something stops us from doing it further than L8. That's 4. And here LCS4 is the free loop space of the fourth sphere divided by S1. We will take the homotopy quotient by S1. So this is, yeah, LS. Well, maybe this is actually for any space. So LX will be a free loop space, a space of continuous maps from S1 to X. And so then we can always want it out LCX. Yeah, X is LX divided by S1. But S1 rotating the source S1, and so it's basically that why does one want to consider such a weird space? It's basically the space of unparameterized groups. So you want to one out by, say, diffeomorphisms S1, or maybe orientation preserved diffeomorphisms of S1, but it's a homotopy equivalent to S1 as a logical group, or yeah. And so it's practically the same to model out with homotopy theory, the same to model out by D plus S1 or by S1. And so this is like parameterized groups. Sometimes they're called equivariant groups, equivariant group space. But maybe because Hisham Sasha is also a co-author of Urs Schreiber, the author and Cat Lab. So now it's official, like where do you look up the most common terminology on Wikipedia, but Wikipedia doesn't have those spaces. So then you go to search, make a search on the internet, and you end up in the lab, and there it says these are called cyclic loop spaces or cyclifications. So this is cyclic loop space for S4 or a cyclification show this. And then you iterate this construction. So for any space, you can consider the corresponding simplification, and then you take the simplification of the simplification and you get a sequence of spaces. And those spaces turned out to be also related to, in a nice way, to the root system of type EK, in the sense, for example, that the torus keep one-dimensional split real torus. So I don't know how, what is a good notation for it. So this is basically the M of R, the real. Well, I want to think of this as a real multiplicative group. That is the multiplicative group defined over the reals, but you can simply think of it as the real numbers minus the origin considered with respect to multiplication. So the multiplicative group of non-zero real numbers and raised to the power q plus 1. And so this is, it turns out to be the maximal. So we proved with the Sasha, so that was one of the theorems, the maximal, but this is the maximal R split torus in the group of automorphisms, let's say call it H odd of L, C, K, S, 4. And actually the same groups for arbitrary even dimensional spheres. So there is no difference really in there. But we wanted S4 for the reason of an explicit connection to physics. So really what we had is an explicit connection to physics. I will tell you in a second what it is, but first let me mention in this relation to root systems. And so yeah, so we proved first of all that the maximal split torus in this group. Yeah, this group of this is the group of homotopic classes of self homotopic equivalences, self-rational homotopic equivalences. So I should put somewhere Q here of self-rational homotopic equivalences of the space. So you consider self maps of the space which are rational homotopic equivalences, and then consider it gives you an algebraic group, and well, it becomes an algebraic group if you use minimal models. Then homotopy classes of self-homotopy equivalences is exactly the group we are talking about. Turns to be an algebraic group, and then another thing is that, well, I mean, it's not a big deal that you have this torus, but you can likewise find a root system in its Lie algebra, if you wish, which is just R to the power k plus 1 as a real vector space, and this is what we are doing there. So this is what we've done there. Also, yeah, it's related and well, given rise to the root system of type EK. Now, the nice part of the story, I mean, it's not maybe so excited to have another sequence of spaces related to the same combinatorics, but the nice part of the story was that we had those algebraic quality was related to explicitly to physics. Whereas so precisely myself. But whereas algebraic geometry, well, the algebraic topology in the sense of rational homotopy theory, so rational homotopy theory that we do, as you can feel, because of what group we consider here. So through rational homotopy theory, those simplifications of the four-dimensional sphere that we have here, we related physics to algebraic topology explicitly, whereas the mysterious duality of the physicist only related mysteriously the algebraic geometry of to physics. And of course, what comes out of our group is mysterious connection between those spaces in topology to the Delphi circles. We still don't know, but we have some idea of this. Now, the explicitness of this was the following: that if you have so explicit relations. Okay, so it's each space, well, good enough space to important path connected space in rational homotopy theory gets assigned an algebraic model called the minimal Solomon model. And this is the space, and here M of X. That's a DGC, differential graded community algebra, satisfying certain conditions. And this minimal solid model is determined by the space up to isomorphism. In the sense, it's determined by the rational homotopy type of this space up to isomorphism. And it's it gives you the solution of the ultimate goal of algebraic topology, to be able to create algebraic invariants which completely describe the space. And so this differential graded cognitive algebras describe spaces up to rational homotopy, like those minimal solid models up to isomorphism describe spaces up to homotopy in any way. So that's a nice story. And so the explicit relation to physics is the following. If you take, for instance, S4 for X, and then take the Solomon minimal model of S4, it's the first exercise you do in rational homotopy theory is to show that it's given by two generators before, which comes out of the it should be a cohomology. So out of the fourth cohomology generator of the fourth cohomology group of the sphere, and G7, which is there for creating sort of for creating the yeah, to create a free algebra. So if some of the minimal model should be free as a graded community algebra. And so the point is that DG4 is 0, as you expect from the generator of the fourth cohomology of the space. But DG7 is something that resolves the relation that in the cohomology algebra G4 squared is 0, and so you want to resolve this relation by adding a new generator and create degree 7, whose boundary is G4 squared, so that you create a free as a graded algebra algebra. So it's a free algebra on one generator of degree 4 and one generator of degree 7. It's a free graded cumulative algebra, and then which satisfies those relations. Now, if you can actually put any constant in here, it wouldn't change the thing, it wouldn't change the isomorphism class of this algebra, any non-zero constant. And if you put -1/2 then you get a connection to physics. Namely, these are like if you ways now this have different interpretation in physics. So these are the equations of motion of 11-dimensional supergravity, which is the infrared limit of M theory. So basically, you drop a lot of stuff that you don't need in M theory, and what's left is supergravity. Or in other words, M theory is based on supergravity, based on 11-dimensional supergravity. And these are the equations of motion of 11-dimensional supergravity. And they happen for those GIs are elements of the round algebra of the 11-dimensional spacetime, which you think of as a manifold 11-dimensional spacetime. And these are just represented by differential forms, and then you have those forms are basic fields of 11-dimensional supergravity, and those equations tell you that, well, there is one equation which I can add, which is not part of the homotopy theory, the Hodge star equation. So this is, and to define the star, you need a metric, so this is where the method, basically gravity comes in. You would have a metric on space time, and you sort of add some stuff. You want to have those equations satisfied, but sort of these two equations are more basic equations. On top of them, you can always add this extra equation, which depends on the differential geometry of the space, but the topology is captured this way. And so, but the amazing thing is that when you start doing simplifications of S4, iterated simplifications of S4, you get more and more complicated solid minimal models of them, they're still described as some generators, and then the differential is defined on the generators. This defines the differential everywhere, and the equations for the differential would be then exactly the equations of motion of those reduced dimensional reductions of the 11-dimensional supergravity. So you get further and further reductions to smaller dimensional space times, and there the equations are just replicas of the equations that you get from minimal solid models. So that's our math physics side of this theory, but there is also a math side which actually deals with new structure, finding new things about those significations of group spaces. For example, we found the 27 lines on L6 on the 6-fold signification of S4. So that's it's still the old work. So here we have 27 lines on L6 of S4, and those are actually elements of pi 2. Rational by 2, some 27 elements defined up to a scalar, in Q. Each is defined up to a scalar in Q. In P2 in pi 2 of L6CS4. And so pi 2, an element of pi 2, we thought of as element from the sphere, which is the same as CP1 to the space. And so these are indeed like complex, if you wish, complex lines in the 6-fold signification of S4. Now it's also the dimension. Yeah, the dimension of this. This is rational. Second homotopy group. its dimension is actually 27, but still it has a distinguished decomposition into lines, into the direct product of 27 lines. That's the point. And all of this such things are possible because we have a root system hidden, or we have election of the torus hidden. So everything breaks into weight spaces. So this 27-dimensional space breaks canonically into weight spaces. Each we prove that each is of dimension 1 over 2. And so this way we get 27 lines in a way on the sixfold signification of S4. Okay, so this is an introduction and a review of our previous work. So now I'm ready to dive into say more about our new work. About the acceptable symmetries. So, do you have any questions to what I have said so far?
Is there any significance to the fact that you're seeing rational stuff appearing here, whereas on the physics side, it's the same like real and like information about real stuff?
Yeah, so really, because we wanted to have a connection to physics, we were talking about real, what do they call it? Rational homotopy theory over the reals. So you can do rational.
Not allowed to call that real.
Huh?
Not allowed to call that real homotopy theory.
You would be the first person to object. Yeah, but it's a real homotopy theory that we actually do. Okay, yeah, I mean, we deliberately do real homotopy theory, even though, like, just if you work with those spaces, everything works over the rationals. But we deliberately want to do real homotopy theory because here is the Rama algebra of the space-time, so it's all over the reals, and then it's actually as long as you have differential graded commutative algebra, which is what this is, over the reals, with two elements, one in degree 4 and one in degree 7, satisfying those equations, then it's immediately by some rational homotopy theory over the reals nonsense gives you a map from well, defined up to I don't know, uniquely in some way in rational homotopy theory from so this is 11-dimensional space, then we call it X. It gives you a map from X to the real realification of S4. So it's like the rationalization of S4 is a space that is rationally homotopy equivalent to S4, but whose homotopy groups are all rational vector spaces. And this is a similar gadget to Q replaced by R. So since this algebra is over the reals, you can't really afford to put Q here, but it's all right. And so it gives you a map so that basically those G4 and G7, which sit here in the Ram algebra, they pull back to the rational what we call the rational differential forms on X. There is notion of rational differential forms on every topological space done by doing the simplicial, the singular simplicial realization, and then in each singular simplex you consider polynomial differential forms and the rational coefficients, and it's algebra that you create out of weights, and this is one of the basic constructions of rational. And so, so you get a map so that those G4 and G7 map to those little G4 and G7, which are elements of your minimal model, Salomon minimal model. And the same happens further on, like X maps to S4, right? Like when you pass to significations of S4, the significant space of S4, then you get reductions, maybe, reduction meaning reductions being like X divided by S1, well, it should be divided in ordered sense, minus the L C of S. In canonical so case, with this map, if you look at this map, if you assume that there is an action of S1 and X, then which was assumed when you do those dimensional reductions in physics. And so you have space-time map into S4 under 11-dimensional gravity, supergravity. Then when you reduce the dimensions, it means you assume that there is an action of S1 on X, and then it immediately this is a 10-dimensional space-time then, and it maps naturally to the signification of S4. And this is some kind of a junction, maybe represented as some kind of a junction in categories. Every maps between spaces here are equivalent maps like this in the category of spaces over PS1. So there is some kind of a junction of two functors between the category of logical spaces and the category of logical spaces over PS1, which allows you to go back and forth between those maps. This junction was discovered by Sasha and Schreiber, actually, or was described by Sasha and Schreiber. It's really a pretty simple-minded statement, but very important here. Now, yeah. So, what about exceptional symmetry? Symmetry. Maybe, yeah. So the title was already there. So maybe let's talk briefly about the rational mathematical theory of real spaces. Significations, functions, and verifications. So there is the construction theorem of the Poirier coming from the golden times of rational commutative theory in the 70s. Poirier and Bulgaria. No, actually it's in the 80s, but it feels like it's like a theorem from the 70s. Yeah. So, well, there was in the 70s there was a theorem by Poirier and Sullivan about the rational commutative, describing the rational commutative type of the free loop space. So, yeah. So maybe I should actually add this to, yeah, and get the same Poirier. Sullivan. Poirier is one person, so this is when this is 1970s. So the first is the theorem. The older theorem is that if you have X in your important, well, they usually want to simply connect. So connected, actually generalized to important space. Simple connected space. Then it's with minimal cell, with the cell and minimal model being identified as well, U V is in graded vector space, graded vector space, equal to the sum of the n is n greater than equal to 2, because we think of simply connectedness. The sum differential, then how to describe the rational homotopy type, that is the minimal model, the sum of the minimal model of the free loop space. The way to do it is that this will be described by the algebra which you take V, and then another copy which might be denoted by SV, another copy of this vector space of generators, and define a certain differential df on it. So df on S V, well, S little v. Let me do it like this. Yeah, so first of all, we need to define the gradient. So when V is in V, denoted by the symbol S with this pointed element of S, and the gradient of SV is the gradient of V minus 1. The degree of SV is the degree of V minus 1. So you get a copy of the same gradient space, but shifted. And probably S stands for suspension, while really this is desuspension, as far as I understand, because like an element of degree 3 in SV will become degree 2. Okay, and so the differential works like this, like S of dV. So dV is an element of the polynomial algebra on spanned by V, or symmetric, created symmetric algebra spanned by V. And oh yeah, I wrote Q of writing things down like I was doing for generators. Probably it's better to call it S of V plus SV. And so here, so meaning this the greatest symmetric algebra on this greatest vector space. So this was also yes. Nobody use the standard notation. The symmetric greatest symmetric algebra on greatest vector space. So it's a free greatest symmetric algebra. All right, yeah, so this differential is like this, but dv becomes a polynomial by the conditions of what it is. Well, in general, it becomes a polynomial in V, an element of the symmetric algebra in V, and so you extend, so dv is not an element just of V, but you extend S extended as to S of V as a V negative 1 derivation. The square is uniquely extended this way, and then you get this condition. Yeah, and then this is how you define the differential, and then df of V becomes just dv. I mean, it's defined as dv for elements V in what generators coming from the old generators like this, from the new generators like this. Then the second part is what happens for the signification. And I think the simplification, so under the same conditions now, M, and this is the theorem of Vigepori in Bulgaria, that MLCFs is identified as the symmetric algebra on V plus SV, and tensored with the polynomial algebra on one variable W. So the thing is that dc of V, well, let's say start with SV. dc of SV is the same story, the same as df. Oops, df. Then, so this is then dc of V is the df of V, which plus W times S d of V plus W times S. So something as the dc of W is 0. So this is the description of how you create out of given a minimal model of the space X, and how you create the minimum model of simplification from it. And with maybe with the right theorem of so decided to finish this thing. Theorem study. So is that if you consider toridification, this is something new, and I asked this question when Alexander Berglund was giving a talk at the seminar a few months ago, remotely from Sweden. I asked him this question, what he knew, what the minimum model of the toridification would be, and he said that he would, that he didn't know that he would think about it, and never returned to me on that subject. So we needed to prove it ourselves. So the toridification is obtained by, of course, you can iterate this construction, and so you can see what happens when you do the n-fold 3-loop space. But instead of doing iterated LCK, we might be also interested in doing the toroidification. So CKX is maps from the torus S1 to the K to the X, modeled out by the torus. That's the toroidification. And so the theorem is that we give a model of this toroidification. So M T A X is and it's not a trivial theorem because it's not the toroidification is not the same as k-fold simplification. It's very different. Only for k plus 1 it will be the same. K plus 1 C1 of X is the same as LC X, but when it goes to this, but it becomes a little bit more symmetric than the k-fold simplification. And so this is generated by S as a symmetric algebra on V plus R of Q of S1 and of SK. And then they have a similar meaning as that. So you can think of this V plus SV as V tangent with Q of S, where S is a degree -1 generator, and of course, and this is the polynomials of this, so it's just 2 copies. The exterior algebra generated by S is just V plus SV.
Do you have the V out front then, or is that get folded in?
Oh yeah, sorry, it shouldn't be up front. Yeah, plus non-tensor with U of W1 W K. Differential. It's a similar story, but the thing is that so we first of all prove that this is a minimum model with a certain, we give an equations for DC, but I don't think it's very insightful if I write them down. But another part of the theorem is that it also has like the minimum model has T K, which is GM R Tk plus 1 to the power K plus 1 is the maximal. That is the idea is that the maximal torus split, maximal R split. Well, this Q is this Q model. Q split torus of font and TK. X font the Morton group in the category of differential gradient convergent algebras. And this automorphisms of the self-minimum model, because of the premises of rational homotopy theory, is the same as the self-homotopy equivalences, rational self-homotopy equivalence of the space time. So homotopy. And so yeah, and so this is another part. So first, the identification was differential is done. This is a similar story to the k-fold simplifications. But the thing is that this thing has much more symmetry. So the third statement, I want to write it down here because going to be done in a few seconds. The last symmetry is that the last part is that the rational Leaf form. Well, we can get this point of the Lie, of the Lie algebra of type EK has a natural action on M EK. And this is, so of course, its torus is acting. This is the torus of such, of course, you can integrate this action to an action of, say, a simply connected Lie group, corresponding Lie group of materials. And the torus is the torus of this group, or you can say the Lie algebra of this torus is the Cartan subalgebra of this. Well, it's a little bit larger. It's like a one-dimensional extension of the Cartan subalgebra of this Lie algebra of type K. So there is already an action of the maximal torus and split torus, and the Cartan subalgebra of this algebra on this because of what we've done. Well, earlier it was about cyclic, like iterated simplifications of S4. Now it's about the storidification. Actually, the storidification has more symmetry in it because you see those pieces of S1 are more on an equal footing. And because of this, there is more symmetry in it. And we find the symmetry that those spaces admit those rational, in rational commutative theory, this rational commutative type of those storidification admits like a symmetry of type EK. And this is, it's kind of also inspired by physics, because in physics, physicists also in the relation to supergravity and its dimensional reductions consider some actions of define an action of the Lie group, of the corresponding Lie group in the algebra. Again, physicists work over the algebras, we work over the algebras too. So exactly. So this is what we have been doing, and this is sort of a glimpse on the new pieces that we have been working on.
Right, thank you. Do we have any questions?
I get a little bit nervous about like taking a rational homotopy type and then keeping applying operators or degree minus one to it because of that connectivity.
Yeah. So there is, of course, that's a good point. You're right to be nervous. I cheated as normal in a talk, and so you take by hand the truncation here greater or equal to 1. Of this space, and on the side of spaces you also do a truncation, that is, you take the connected component of the constant map. Like you assume that this is path connected, and then you take connected components each time around, and each time around you start. Well, you do it just once. This storidification. So you take the connected component of X and take the connected component of the metric space. On this side, it results in this.
I've been wondering all this time, does anything actually live in this 11-dimensional supergravity? Like, do we live in 11-dimensional supergravity? As far as we know, and all this M theory and stuff, but presumably it's a theory which may apply to all kinds of variables and things like this, but so far as we know, does it hold up? Is this a viable?
Yeah,
description?
people got a Nobel Prize for that. It's not super.
Well,
It's not super
right,
string theory, huh?
It must be right then.
Which means it's experimentally confirmed. I mean, what, I don't know exactly how you perform such an experiment. Maybe you submerge Peter in the 11th dimension with three of his wives. Yeah. Yeah, so the 11th-dimensional supergravity, like the 11th-dimensional space is consists of the 4-dimensional space-time, the kind of classical space-time, 3 dimensions that you and I see plus 1 time dimension. So you can take this easily, understand this. Then there is this story that there are 6 dimensions sitting at a very small level at like
Small particles.
small particle level, like there is still part of the space, like 6-dimensional space, and this is claimed to be Calabi-Yau threefold, a complex Calabi-Yau 3-dimensional manifold, so that the particles are allowed to wobble in this extra 6 dimensions there. This and this came from string theory, the idea, but still it's I don't know. People were doing before string theory with those high-dimensional generalizations of in supergravity, and that 11-dimensional supergravity is like is 11-dimensional, like it's 7-dimensional extension of the usual space-time, and so maybe it's not really true that we live in this space from the point of view of the supergravity, but the thing is that you add extra dimensions so that to allow supersymmetry, supergravity basically, and so.
I got up to 10, you had 4.
Yeah,
but there.
But so 10 is super string theory, which is indeed not confirmed. So we don't really know whether we live in a 10-dimensional space or not. But at least supergravity is confirmed, and it happens mostly like the primary event is in 11 dimensions, and then you also get dimensional reductions, which I don't know what they mean. And there it is claimed that elementary particles live in 11 dimensions. Also, the standard model, but the standard model perhaps was not really that high dimensional. It was 4-dimensional. But you get some kind of pieces for particles like flavors and such, which are described by representations of specific Lie groups.
I have a non-math question. Like, I'm interested to know what your thought process is when doing such a project. Like, do you like focus on the math and then see where the math takes you and then try to interpret those results into the physics? Or are you guided, like when you said like, oh, in physics, we also have these actions by these Lie groups, so these probably have something to do here, and then you explore that.
Right. Yeah. So yeah, it's mostly guided by the math of it, and then trying to interpret what we obtain. But on the other hand, say when you get stuck, for example, you look back at physics. And you say, okay, they have this, so why not construct something here? That's how I operate. Maybe Hisham is more of a physicist than I, and maybe he operates exactly the other way around. Yeah, for instance, Hisham told me that those, like when you get, remember Tyler asked that you get to negative degrees. When you get to degree 1, you get certain generators, and those generators are called axions.
Are called?
Axions, like, I don't know, from, so if you have, for instance, S1, S2, S3 of G7, which will be there because V contains G7, then it's an element of degree 1, and this is an axion. So everything has an interpretation like axion, I don't know, like elementary particles that corresponds to the axis, I guess, like to the X, Y, X1, X2, X3, X4 axis. I don't know, but these are called axions, and they play an important some role in physics. I don't know how important. And so at first we were working with this model LKC S4 because it has more actions, and we thought that this was great. From the very start, we needed to choose between this model and that. They seem to be very similar, but we needed to choose which one. So this one contained S2 of W1. Now the S, those operators, degree shifting operators, S are in when you do the simplification are also affect those generators because you iterate the construction. And so when you obtain W1 on the first stage, like even this one would contain this, then you can take S2 of W1, and this is W1 was, oh, I forgot to say from the very start here that W2. We could figure this out from this equation of this. Yeah, so this is known to degree 2, this is known to degree 1, this is like an extra action that you get. And Hisham told me that those actions actually are there in physics, sometimes considered. Sometimes people consider what he says more actions like this, sometimes they say that those actions. I'm talking about the other model that is in physics, they have those fields, and depending on how many dimensions you have more fields, fewer dimensions, fields, and some equations of motions for them. And then among fields, they say, okay, we have a field which is like this. They don't denote it this way at all. They just say it's, I don't know, it's a field F1. Well, yeah, of degree 1. And they have different labelings of those, but you can recognize some things, kind of count how many fields they have in physical theories, and he said that these actions are better to have there. Okay, and this is how we look back at physics.
All right, if there's no more questions, let's thank Sasha again. What's Sasha, sorry?
Thank you for coming, and as always, we are happy to have Polish beers to sort of not to allow the Polish beers to die. So I invite everybody for the Polish beers, and invite in the literal sense.
Okay.
Yeah.
I'm passing, I'm afraid. I can't
Yeah.
be with you again until the end of November.
Yeah, unfortunately, yeah, that's bad thing, but you told me last time around